Hello everyone, this is Engineering 245 Dynamics, and this is Professor Lin. This is the very first of several online lectures that I will be posting due to my absence. Okay, I have a family situation that requires me to be out of the country until mid-February, so we will be relying on these online lectures in the meantime. I hope this doesn't pose any problems. If you do run into any situations that I will not be able to resolve for you via email, you can contact Professor Woodke, who is the Assistant Dean of Engineering, and I have listed his contact information on the Blackboard page. Okay, so before we do anything else, let me go right to that Blackboard page. And for those of you that haven't already, please take a look at the first note that I posted up, the first announcement, because there are a few important notes there regarding what's going to happen these first few weeks. Okay. The other important thing that's on here is the syllabus. Okay, and that's also posted up. So if you go to the syllabus link, you should be able to bring it up, and you might want to print out a copy for yourself because this contains a lot of course information. So like always, this has my contact info, my office hours once I'm back on campus, and then a bunch of things related to the material of the course. Okay, so read through this. Just some things to point out here. Right? First of all, the textbook. It is Vector Mechanics for Engineers, Dynamics. So Dynamics is volume 2 of Vector Mechanics for Engineers, and I believe the latest edition now is either the 10th or the 11th. Okay, I really have no preference what edition you use. For myself, I use the 9th edition because I've already worked out a lot of problems from that edition. So those solutions that I've posted up are from the 9th edition. If you go under course documents, okay, you will find the solutions that I've posted up. For those of you that do not have the 9th edition, right, don't worry about that because I've also scanned in all the problems out of the 9th edition. All right, so again, use any edition that you feel works for you. They're all very similar, okay? The only things that might change are some of the problems, and obviously some typos have been corrected. Okay, we will be covering chapters 11 through 17 in this textbook. All right, further on down in the syllabus, you'll see a course outline. Okay, this lists all the dates that we meet and then all the topics that I hope to cover. All right, so you can see on here, obviously, the first few weeks, I've listed those as online lectures, right, of which this is the first. Also on the syllabus, you'll notice that there are 4 exams listed. Right? I will not give you the first exam until I return, and that will be an online exam. Not online, I'm sorry. It'll be a take-home exam, okay, in the interest of saving some time. And then exams 2 through 4 will be in class. Okay, so you have the dates of those exams, and you'll see the final exam listed, right? You'll see how the course is going to be graded, and then of course there are some important notes regarding policies and procedures, so make sure you go through those. Okay, so that's the syllabus and the Blackboard page. So let me get rid of this. And we're going to jump right into the very first lecture. All right, so this is going to be out of chapter 11 in the textbook, and I will be relying on my PowerPoint slides. Okay, these have been converted to PDF, and they're also posted under course documents, so you will have access to those. All right, so let me bring up my first set of notes. Okay, and before we really start talking and getting into details of dynamics, just some background information, if you will. Okay, so dynamics a lot of times follows from statics, but as contrary to what you might believe, these are actually 2 very different classes, okay, 2 very different courses. Statics, as the name implies, and as you all know because it's a prerequisite for this course, deals with objects and bodies that are at rest, okay? So there's no motion whatsoever. And what that means is in your statics problems, there was never a time component, right? You assume that your objects were stationary for the whole time that you're working on your analysis, or that in your analysis you're looking at a single moment in time. In dynamics, we're starting to look at things that are in motion, right? So time becomes important because that object is going to change its motion throughout time. And just due to this very simple fact, okay, these two classes are very different in the way that the problems are solved. So statics, of course, is important in designing structures, right? If you go into civil engineering in particular, statics is a very important part of your curriculum. Dynamics is more required for those that might start designing machinery, right? And anything that moves, vehicles, right? Things of that sort. All right, so on the syllabus, you probably saw some terms there that you were not very familiar with, okay? And we'll start describing what some of those terms are, but there's really no need to get into that yet, okay? All right, two of those terms, of course, were kinematics and kinetics, right? And as I said, we're not gonna get too much into those yet. All I wanna say is kinematics deals with the geometry of motion, right? Meaning it's basically describing the motion of the object. And what do we use to describe the motion of the object? Well, you need time, right? You want to be able to tell its position or its location at any moment in time. And then you want to know how fast it's moving, right? What direction it's moving in, and whether it's slowing up, slowing down, or speeding up. Okay, so those are the kinds of quantities that are used in kinematics to describe the motion. In kinetics, okay, we start worrying about what causes that motion. And of course, you should all know that that's basically Newton's second law, right? Which says if you apply a force to an object, right? If you have a net force acting on the object, then that object is going to have an acceleration, which of course is motion. All right, so these are the two distinct categories of dynamics. And the way we're going to approach our study of this course is we're going to start with particles, right? You might all remember from statics that a particle basically assumes that the object you're looking at can be represented by a single point. And that, of course, is very different from a rigid body, right? Because in a rigid body, you cannot just look at the object as a point anymore. Its size and its shape become important. And you should know what the difference is, right? Or when we're able to treat something as a particle and when we cannot treat it as a particle. Right? The important thing is that a particle does not mean that you're looking at tiny, tiny objects, right? You could be looking at a very large object, but because of the way the forces are acting on it, we can treat that object as a particle, as a single point. Okay, so just as a very brief review. Okay, if I have some object, okay, some random object, random shape, random size, and it's got a bunch of forces acting on it, right? These could be forces in 2D and 3D, it doesn't matter. So I'm just going to draw 3 forces here, but it could be a lot more than that, right? When can you treat this object as a single point? So think back to statics, right? And hopefully you all remember that there was something called a principle of transmissibility, which says that you could slide any force acting on this object along its line of action. Okay? You can move that force anywhere you want along that line without changing the problem. So what you do is you apply the principle of transmissibility to every single one of these forces, right? And you try to slide them to make a determination of whether they all intersect at a single point, right? And the way I have this drawn, they pretty much do intersect at this point. And if that happens, then this object can be treated as a particle. If they don't, then you cannot treat this as a particle, and this would be treated as a rigid body. Okay? So what's the importance of that? Right? Well, if you take the sum of moments about this point, right, in the first case, in this case, where all the forces intersect, you should know from statics that you have 0 moment about that point. 0 moment means 0 rotation, right? And if an object doesn't rotate, then you don't need to worry about its size and shape. It just keeps moving without rotating, right? If it were to move. So in that case, you could treat that object by simply looking at that single point. And usually this point is the center of mass, right? Because the weight can be assumed to act through the center of mass. So the weight obviously would be one of the forces acting on this object. If the forces do not all intersect at the center of mass, then what do you end up with is a moment about that point. And a moment now in dynamics, right, if you have nothing to hold it in place, a net moment is going to cause a rotation. And a rotation is motion that has to be described and analyzed. So in that case, this becomes a rigid body problem. All right, so with that brief review, let's go back to our discussion of how we're going to approach our study of dynamics. All right, so what we do is we first start off with the simplest type of problem. That would be a particle problem, right? And we start looking at kinematics, or describing the motion. We don't care why this object is moving, right? We only want to describe its motion. All right, so we do that. That's the first part of this course. And then we move on to kinetics and looking at the forces that cause this object to start to move. All right? And you notice that there's nothing about moments at this point because this object now is not going to rotate. Then what we do is we move on to a collection of particles, right? We call this a system of particles. And that's basically just extending the kinematics and kinetics of particles to just more than one particle. All right? And then in the second part of this course, we start looking at rigid bodies. We start looking at kinematics of rigid bodies, and now we have to describe how the object is rotating in addition to how it's translating. Okay? And finally, we end up with kinetics of rigid bodies. Okay, so that's exactly how this course is going to proceed. The first half, what a lot of you are going to find is that you've seen a lot of this material before in physics. All right, so for those of you that this is really a review for, don't get too complacent, because in the second half, we might start looking at things that are going to be new to you. Okay, so just keep that in mind. All right, so now that that introductory material is out of the way, we're going to start talking about kinematics of particles. All right, and the very simplest type of kinematics is what we call rectilinear motion. Okay, like this term that I've got underlined here. Rectilinear motion means motion along a straight line. All right, so you have an object that just moves back and forth along a straight line. Next lecture, what we start looking at is curvilinear motion. All right, and now all that means is the object is going to follow a non-linear path. It could move in any path. It could follow any path at once, right? In space. Doesn't have to be 2D, right? It can be in 3D. All right, so we'll start very simply. Okay, and let's start talking about how we're going to describe motion, right, of an object that's just moving back and forth. So I had said earlier that in order to describe the motion of an object, there were certain quantities that we needed, right? So if you think about this, right, being able to describe the motion of an object means, what it means is that you have to be able to predict or be able to describe exactly how this object is moving at any moment in time, right? So what we do is we start observing this object at some point in time, and we're going to call that time t, right? T is our variable that denotes time. So we're going to start looking at motion at t equal to 0, okay? And then at any other moment in time after that, it could be t equal to 1 second, t equal to 5 seconds, whatever, right? At any moment after that, we have to be able to locate that object, right? Be able to precisely predict where that object is going to be. We have to be able to predict exactly how fast it's moving and in what direction it's moving, right? And then we have to be able to predict whether it's speeding up and in what direction, and whether it's slowing down and in what direction, okay? So these are the kinds of things that we need, right? So if we start thinking in terms of these quantities, you can imagine now that in order to locate and find the position of this object, we need a point of reference, okay? And mathematically, what that means is we have to define an origin. You first define a coordinate system, and you have to define the origin of that coordinate system. Now, in rectilinear motion or one-dimensional motion, right, motion along a straight line, it's very simple, right? You choose some coordinate axis. Usually people choose x, right? If that motion is horizontal, they choose y if that motion is vertical, right? And we just set up, say, an x-axis, okay? So something like this. I decide that I'm going to choose this horizontal axis as my x-axis, and then I just arbitrarily choose an origin, right? That's this point that's labeled O on here, right? You've all done this before in very simple high school mathematics, right? So you choose your origin, and then you have to choose a way of measuring, right? So you just choose a scale. You might decide, okay, I'm going to choose, if that object is not moving very far away, right? If it's not displacing very much, then you could use an exact scale, meaning you might want to measure its motion in terms of meters, right? Maybe even centimeters, or in the US system, right? Feet or inches. It doesn't really matter, okay? So once you decide on an origin, once you decide on the scale, then in order to find the position of that object, all you do is you measure, right? So when when your object, as is shown here, is 5 meters away, right? You say x is equal to 5 meters. That's your position coordinate, if you will, right? Or your position variable. And of course, in one-dimensional motion, it's very easy to kind of designate whether your object is to the right or to the left of your origin, right? We just use our standard convention. If it's to the right, we say that it's a positive x position. If it's to the left, we say it's a negative x position. Okay, so that's the first quantity that we need, right? Is position at any moment in time. All right, so what's next? We now have to be able to tell whether that object is moving and in what direction, right? Is it going right? Is it going left? And how fast is it going? Okay, so what we're going to do, okay, is come up with a variable that we are going to call velocity, right? So let me come back to this. This is not needed at this point, okay? So we're going to define something called velocity, right? And a velocity, again, is going to tell you exactly how fast you're moving. The way this works is we start off with a definition for average velocity, okay? And average velocity is the amount of distance that your object moves over some period of time, right? So basically what you do is, let's say we're tracking this object, right? It starts off at x is equal to 5 meters, right? Ends up at x is equal to negative 2 meters. And maybe that happens over the course of a second, right? So the way we're going to define an average velocity is that it's your change in your x-coordinate. So in our case, right, that's a negative 2 minus 5. That means negative 7 meters divided by the amount of time that passed. In our case, we said it was 1 second, right? So our average velocity during that time is -7 meters per second. Now, how useful is something like this? Okay, well, it's not very useful, and here's why, right? If that object, over the course of that 1 second, were to move back and forth, rather than simply moving left, maybe it moved left some amount, it moved right, moved left again, then moved right, before it finally ended up at -2 meters. If it did that, right, it didn't actually displace, it didn't actually travel 7 meters. It might have traveled a lot more than 7 meters, right? But it just backtracked a lot of the time. So when you say that its average velocity was 7 meters per second, I mean, what does that really mean? Not very much, since it moved all over the place, back and forth, okay? So, in fact, right, if you think about this, if you have something that starts off at x is equal to 5 meters, it moved back and forth, and it ended up back at x equal to 5 meters, over the course of, say, 10 seconds, what is its average velocity? It's 0, right? So the average velocity doesn't tell you very much. What we want, okay, is we want to know precisely how fast that object is moving. This will be kind of like the speedometer in your car, right? Your speedometer tells you exactly how fast you're moving at that exact instant, okay? So that's really what we want. So how do we get that? Well, that's what we call an instantaneous velocity, right? And the way we get that is very simple. Instead of looking at large intervals of time, delta t here, we start letting our delta t get smaller and smaller. We start looking at smaller and smaller intervals. In fact, right, we're going to let delta t approach 0. And of course, you all know from calculus that this is basically taking a limit, right, of delta x over delta time as delta time approaches 0. And in that case, what this becomes is a differential, right? It's a dx dt. That's our velocity, v. Lowercase v is equal to dx dt, okay? And if you do that, now that gives you your instantaneous velocity, or your velocity at that exact moment in time, right? And this is very simple. In one-dimensional motion, this is very simple. If your velocity is positive, then that means you're moving in the positive direction, right? With whatever speed that that differential gives you, okay? And if it's a negative, then it means you're moving in the negative direction, right? Simple enough, right? Okay, so that's velocity, right? And that's obviously an important quantity that's used to describe the motion of an object. All right, so let's move on. The next thing that we need, right, is we need to describe whether this object is speeding up or whether it's slowing down. And the way we're going to do that is very similar to the way we came up with this idea of an instantaneous velocity. Okay? We're going to start defining something that's called an average acceleration. Okay, I'll get back to that again in a little bit. So an average acceleration now is going to be defined as a change in velocity over some change in time. And again, this is not very, this doesn't tell you very much, right? So what we want to do is we want to let the time interval go towards 0. We take the limit again, right? And as shown on the bottom here, what that means is our instantaneous acceleration, we use lowercase a, right, is dv dt. Your change in velocity with respect to time, right, differential, and or it's the second derivative of your position with respect to time. Okay, so these are the two important definitions that we have. Okay, you have velocity, it's dx dt, acceleration is dv dt, or the second derivative of x with respect to t. Okay, now you might look at these and say, well, how do I use these, right? I mean, these are nice, simple mathematical equations, but I can't really do anything with these unless I have a function of x, right? Everybody should be able to tell from this that in order to use these equations, you need really x as a function of time. Okay, so we'll get into how you're going to get x as a function of time, but let's say you do have some x as a function of time, right? And that's our example here. Let's say you find that x is equal to this, this function 6t squared minus t to the third, right? And the nice thing about having a function is you could always plot it out. Like you see here, right? You plot x versus time. X is on the y-axis, time on the x-axis, right? That just kind of gives you a visual, if you will, of how this object is changing its position, okay? So if we have x as a function of time, you can take a look at this function. It's very easy to differentiate this function, right? So with that, in order to find velocity, you just differentiate and you get 12t minus 3t squared, right? And the nice thing about having these functions, right? Remember I had said that kinematics means you want to be able to predict where this object is, where it's moving, right? How fast it's moving, and all of that. You want to be able to predict all those quantities at any moment in time. Well, having a function of time means you can make that prediction, right? Because if I have this equation and I want to predict, or I want to know precisely where the object is going to be at, let's say, t is equal to 20 seconds, then all I need to do is plug in 20 for t, and I could get out exactly what x is. Same thing for velocity, right? If I have this equation for velocity as a function of time, and I want to know how fast this object is moving, then I just plug in whatever time that I'm interested in, right? And I can go ahead and find its exact velocity. And of course, then we could do the exact same thing for acceleration, okay? So x was 6t squared minus t cubed. We differentiated once to get 12t minus 3t squared. Differentiate again, you get 12 minus 6t. That's acceleration as a function of time, okay? Now, let's go back to acceleration for a second, right? Because we had said that your velocity, as far as one-dimensional motion goes, right, your positive or negative sign tells you exactly what direction your object is moving. Well, acceleration is a little trickier, okay? Because a positive or a negative acceleration can have different meanings, okay, depending on the situation. So make sure you understand these four different scenarios, the four different possibilities, okay? So when we say that an object has a positive acceleration, okay, the obvious thing that most people think of is that that object is going to speed up going in the positive direction, right? That's the left case here, right? This left situation. And that's, of course, correct, right? But a positive acceleration can also mean, right, and you could prove this mathematically, it could mean that your object is slowing down as it's moving in the negative direction, okay? And as far as a negative acceleration goes, right, most people probably would think in terms of, well, it's decelerating, right, meaning it's moving in the positive x direction, but it's slowing down as it's moving in the x direction, right? However, a negative acceleration now could also mean that your object speeds up going in the negative direction, okay? So make sure you kind of understand the differences between these four cases. All right, so let me now talk about how you're going to come up with these functions. Okay, because the whole idea of all this math, right, that we develop, all these equations and these methods, is you have to be able to apply these out in the real world somehow. Okay, so in the real world, okay, let me give you a scenario here. You are an engineer, right, or maybe a physicist, and you are trying to predict some device you've invented, right? Maybe you develop some device, and you know this device just moves back and forth along some track. And what you need is you need some way to predict, right, the position, the velocity, and the acceleration of this object, this device, at any moment in time. So if you think about how you're going to do that, right? You know from what we just talked about that what you really need is some function of x as a function of time. Because you know once you have that function of x or position with respect to time, then you simply need to differentiate it once to get velocity as a function of time, and then twice to get acceleration as a function of time. Okay? So how are you going to do that out in the real world? Okay, well, hopefully some of you came up with this idea that you would probably just run some kind of an experiment, right? So here's probably what you would do. Okay, I've got this object moving back and forth. What I'm going to do, right, especially these days with sophisticated equipment, I'm just going to set up a nice video imaging system, right? And all it's going to do, right, is it's going to maybe track or take video of this object that it's moving back and forth. And from these images that I capture, these video images that I capture, I should be able to measure exactly where that object is, right? And I've also got a timestamp on all these images that I've captured, right? So from all of that, what I end up with is a lot of data, okay? And this is what that data might look like, okay? I'm going to have at time t, right? I'm going to have some column for time. So this is going to be in seconds, right? Let's say. And I know from the time that I start tracking that object, I'm going to call that time t equal to 0. And then maybe I capture a video image every second. So I've got 0, 1, 2, 3, right? Maybe all the way down to, I don't know, 1,000 seconds, right? And then I have noted down the corresponding x positions. Okay, so maybe this is 5 meters, and then it moves to 7, then 10, then 15, right, and so on and so forth. Okay, and once I have all this data, right, and like I was saying, there's such sophisticated equipment available these days that this could all be automated for you, right? Once you have all this data, then all you need to do is you use some kind of software, right? Excel comes to mind since it's so readily available. Everybody uses it. You plug this into Excel, right? Plug your data into Excel, and you plot it. Okay, you create a graph in Excel that's going to be time t on the x-axis, your x on the y-axis. You plot it out, right? So maybe you've got a bunch of points. Whatever, I'm just making up something random here, right? And then Excel has a curve fitting feature that basically tries to fit a mathematical curve, a mathematical equation through your data points. Okay, now it doesn't have to pass through all the points, okay, right? Because there's always going to be a little bit of error or a little bit of variance, right? But you try to fit a best fit curve through these points, and then Excel will give you the equation of this curve. And guess what, right? That equation is your x as a function of time. Okay, so usually in a lot of real life situations, that's how you come up with this function, x as a function of time, right? X in terms of time. And once you have that, now you can predict your velocity and your acceleration. Okay? So hopefully that painted a clear enough picture for everyone, right, on how you're going to make use of these two simple definitions, right, or these two simple equations out in the real world. All right, so let's move on, okay? And probably I would say maybe 80 to 90% of the time, all right, that's what you would do, okay? You have this object that you're trying to track, and you use some kind of equipment to come up with times and the positions at those corresponding times and the corresponding positions, right? And once you have that, you curve fit your data, come up with your equation for x as a function of time, and once you have that, it's very easy to get velocity and acceleration as a function of time. All right, now here's the problem, okay, in some cases. There might be situations that you run into out in the real world where it's difficult for you to get position as a function of time, right? It might be much easier to measure something else instead of position, and maybe instead of time, right? It's easier to measure something else, right? So we're gonna look at 3 other situations that you could encounter out in the real world. Okay, so the case where you do have position as a function of time is what I would call the base case or the trivial case, right? It's a case where everything starts from, but now we have 3 additional cases in addition to that. So here's the first case that you might run into, right? And this is going to be the easiest of the 3 additional cases, right? Sometimes you might have acceleration as a function of time. Now you're going to ask, well, when would that ever happen, right? So let me try to kind of give you an idea of when this might happen. There is a device out there, right, that some of you might know of called an accelerometer. Okay, and an accelerometer, actually, accelerometers are pretty much in all smartphones these days, right? But an accelerometer, if you want a simple description, I mean, basically it measures acceleration, okay? And, you know, so imagine you have this object that's moving around in a straight line, and you've attached an accelerometer to it, okay? And now, maybe this accelerometer is sending out a signal, right? It's a wireless accelerometer, and you've got a receiver attached to your computer, and all it's doing is receiving the acceleration data that's being put out by your accelerometer. So instead of having a bunch of data where you have positions and times, now what you have is a bunch of accelerations at different times. Okay, so here's just to make sure we're all on the same page here, right? You now have, for different times, you now have basically for your data, you have times and then corresponding accelerations. So 0, 1, 2, 3, 4, right? And you have a bunch of acceleration values going down there. And what do you do with this? You plot out time on the x-axis, you plot out acceleration on the y-axis, right? You plot your data point, you fit a curve through it, you use software to get an equation for that curve, and now instead of x as a function of time, right, what you have is acceleration as a function of time. Now, if you have acceleration as a function of time, I mean, that's fine, right? Now you could predict what your acceleration is at any moment in time. But how do you predict what your velocity is? How do you predict what your position is at any moment in time, right? So that's our goal. Keep in mind that in all these cases, our ultimate goal is to get position as a function of time, because that's the simplest equation that we hope to have. Once you have position as a function of time, right, it's easy to differentiate to get velocity and then acceleration. Okay, so that's our ultimate goal. So how are we going to get all the way down to position as a function of time in this case? Well, let me illustrate this in the form of an example, right? And as I said, this is the simplest of these 3 additional cases. So a lot of you are going to know exactly what to do here. Okay, but let me just come up with something here, right? So let's say acceleration we found after going through our data fitting is equal to 3t squared plus 4t plus 2, right? So here's what we do. I take a look at this and I say, well, I've got acceleration and I've got time. I know I have 2 equations, if you will, or 2 definitions that are available to me. I've got v is equal to dx dt. I've got a is equal to dv dt, right? Which one of these, or is either of these going to be useful to me, right? So I look at this and I say, well, this one has basically three variables in it, right? I've got acceleration, velocity, and time. And in my actual situation, I've got 2 out of the 3. I've got acceleration and time. Whereas the velocity definition, right, has 3 variables in it, but only time is part of that equation. Okay, so this one is out. This one is not going to help me. Okay, so the acceleration equation is what's going to help me because it contains 2 out of 3 of those variables. Okay, so let me rewrite that. I have A is equal to 3t squared plus 4t plus 2, and I'm going to use a is equal to dv dt, okay? And this is a differential equation, right? But here's the great thing about linear differential equations, right? Calculus says that if you have a linear differential equation like this, then you could treat it like any simple mathematical or a simple algebraic equation, meaning, okay, you could cross multiply, you could substitute, you could do whatever you might do, even if this were a simple mathematical equation. So what I'm going to do is I'm going to cross multiply here. I get a dt is equal to dv, right? And the nice thing is I look at this and I say, well, a, right, I have as a function of time. So I put that in. I get 3t squared plus 4t plus 2 times dt is equal to dv. What do you notice about both sides of this equation? Well, both sides are integrable, right? Both sides can be integrated. So that's exactly what we're going to do. I'm going to integrate. Okay? Now, there is a problem that comes out here, right? That comes up here. If you integrate this, these are indefinite integrals. So what do you end up with is a constant of integration on both sides. Now, you could bring one of the constants of integration over to the other side to leave you with just one constant, right? But still, you do have this uncertainty, okay? So what that means is in every single one of these problems, you're going to need what are known as initial conditions. An initial condition is simply basically you have to know what your velocity, what your position, and you don't need acceleration usually, right? But initial conditions then basically mean you need your position and your velocity at time t equal to 0. All right, so let me just make something up here. Let's say in addition to knowing that acceleration is equal to this function of time, I also know that at time t equal to 0, right, that my velocity maybe is equal to 5, and my acceleration, my position, let me erase that. My position might be equal to 10. Okay, now, I'll talk a little bit more about units, right, in a little bit. But these could be any units, right? Time is always in seconds. But as far as position goes, it depends on what system of units I'm using, right? This could be 10 meters, it could be 10 inches, 10 feet, right? 10 kilometers. It depends on the problem, okay? That's not important at this point. You just have to make sure you specify what units you're using if you were working this out. That's a real problem. All right, so once I have those initial conditions, okay, there are two ways of continuing here. I can work out these two integrals as indefinite integrals and then make my substitutions, right? So here's how that will work, right? I integrate, I get 3t cubed. Let me correct this here. 3t cubed over 3 plus 4t squared over 2, and we're going to simplify, of course, right? Plus 2t plus some constant, and let me call that c1, is equal to v plus c2. Okay? These are two different constants of integration. Okay? And of course, like I was saying earlier, since these are two constants, I could simply bring, let's say, c1 over to c2, right? And combine them into one constant. So let's do that, right? I'm going to get rid of c1, and then I get rid of the subscript here. I have one constant of integration, essentially, right? And now, how do I find out what c is? Well, I start making use of my initial conditions, right? I know that at time t equal to 0, right, my velocity is equal to 5. So I just plug in, right, t equal to 0. That gives me 0, 0, 0. So this is 0 is equal to whatever my velocity is plus 5. okay? And what does that mean? It means v, I'm sorry, let me correct this here. Okay, I get 0 is equal to velocity is 5 plus c, right? And then what does that mean? It means c is equal to -5, and now I can say, right, let me write that here, I could solve for v. I could say v is equal to, I simplify now, right, this is t cubed plus 2t squared plus 2t, and then I bring the c over, right, plus 5. Okay, and there's velocity as a function of time. Okay, does that make sense? All right, so what's the other way that I was referring to of doing this? Let me erase this, okay, for now. And let me show you the alternative, which I actually prefer because it's going to be a little quicker, okay? Let me erase all of this. The alternative is to treat these as definite integrals, okay? So I need limits here, right? You know that in order to make this a definite integral, you need limits of integration. And I'm going to go ahead and make use of this, right? So this is the time integration. This is the velocity integration. So for my lower limit, I know that I start with time t equal to 0. And then I'm just going to go to some arbitrary time t, okay, as my upper limit. For my velocity, okay, I need my corresponding limits, right? So when time t is equal to 0, what's my velocity? It's 5, okay? And then at some arbitrary time t, I have some arbitrary velocity v, okay? So if I go ahead and integrate this now, okay, these become definite integrals. My left-hand side is going to give me, and let me skip a couple of steps here, okay? We're not going to go through the full integral and then simplify at the end. This is going to give me t cubed plus 2t squared plus 2t, right? And then that 0 lower limit means there's no constant here. And then this is equal to v minus 5. Okay? And I just bring that 5 over. I get velocity is equal to t cubed plus 2t squared plus 2t plus 5. Okay? So this brings us a step closer. I now have velocity as a function of time, right? I had acceleration as a function of time. I now have velocity as a function of time. I need to go one step further to get position as a function of time, right? So how am I going to do that? So let me go ahead, right? Bring up another page, and let me rewrite that velocity equation that we had. Right? So we have velocity is equal to t cubed plus 2t squared plus 2t plus 5, right? And we want position as a function of time. So looking at this, I now have velocity and time in one equation. I go back to my first definition. That was velocity is dx dt, right? And you can see 2 out of the 3. I have 2 out of the 3 in this equation. Okay, so I cross multiply again. I get v dt is equal to dx. And now I can substitute in my function for v right into here. Okay, so that's going to give me t cubed plus 2t squared plus 2t plus 5 dt is equal to dx. And what do you know? What can you say about both sides? Both sides are integrable now, right? So I'm going to integrate. Remember what your initial conditions were, right? At t equal to 0, we had velocity was equal to 5, position was equal to 10. So I'm going to make use of those limits. I go from time t equal to 0 to some later time t. I go from the corresponding position for x is equal to 10, right, at t equal to 0, to some later x, And now I integrate. This is t to the 4th over 4 plus 2t cubed over 3 plus t squared plus 5t is equal to x minus 10. All right? And now solve for x. Bring that 10 over. X is equal to t to the 4th over 4 plus 2t cubed over 3 plus t squared plus 5t plus 10. Okay? There's my final answer. That's what we wanted, right? X as a as a function of time. Okay, so this is the first additional case that you'll want to be able to handle, right? You'll want to be able to work out. Like on an exam problem, for instance, if I were to give you acceleration and then some function of time, right? Then you should be able to go through this process and give me position as a function of time. Okay? All right. So let's I'm going to erase these pages. Okay, I don't think we need these. Let me erase that other page. We're now going to look at the second scenario, okay, that you might run into. And this would be the case where you have acceleration as some function of position. Okay? Now, again, think about when this might happen out in the real world, right? When would you have a bunch of data points where you have acceleration values and corresponding position values? So here's an example, right? We know that GPS is pretty commonplace these days, right? So now imagine you've designed some device that's got both an accelerometer mounted on it and it's got GPS positioning. Okay, so all this, what your device is sending out, right? This what data it's sending back to you, maybe sending to your computer, right? Who's collecting this data? What the data that it's sending you is going to represent is you're going to end up with a bunch of acceleration values and then a bunch of GPS position values. Okay, so you go through that whole process again of taking those values, plotting them, right, and fitting a curve through them, and you end up with acceleration as a function of position. All right, and let me repeat, right, ultimately you want position as a function of time. So let me give you an example here. And I'm going to use a very simple example, and you're going to see why that this example has to be fairly simple. Okay, so let's say this is 2x plus 3. Okay, a simple linear equation. All right, so how do we approach this? Well, we know that we have two definitions available to us. Right? We've got v is equal to dx dt. We've got a is equal to dv dt. Do you see a problem here? Right? I've got acceleration. That's this. That's from that definition. And then I've got position, right? X. That's from this definition. I need to make use of both of these definitions somehow. And the only way you're going to be able to do that, okay, is to look at what's common between these two definitions. And the common quantity, or the common variable, is your time, dt. Okay, so here's what we do. I take my acceleration equation, acceleration definition, and I'm going to solve for dt. All right, so I'm going to get dt is equal to dv over a. And then what I'm going to do is I am going to substitute that dt into that dt from my velocity definition. That gives me v is equal to dx over dv over a. okay? And you can go ahead and simplify here. Ultimately, what you want to end up with, right, is v dv is equal to a dx. Okay, that's just from algebraically manipulating this equation here. Okay, so what can I do with this? Well, let's go to a new page here. Okay, so we've got a is equal to 2x plus 3, and now we have v dv is equal to a dx. So here's what I do, okay? We have a is this function that I'm going to plug into there. Look what that gives you. V dv is equal to 2x plus 3 times dx. Are both sides integrable? Yes, they are. Okay, so now I can integrate. Remember what this means, right? We need initial conditions. So let's just use these same initial conditions that we came up with earlier. So at time t equal to 0, v is equal to 5, and x is equal to 10. All right, so what that means is at the lower limit for velocity, remember this is the velocity side, right? My lower limit for velocity is going to be 5. I go from 5 to some later velocity v, and then the corresponding position when velocity is equal to 5 was 10, right, to some later x. So now you can integrate. This is v minus 5 is equal to x squared plus 3x, right? And that goes from 10 to x. Okay, so you could, I'm sorry, I messed up on the left-hand side there, right? Sorry about that. This is actually v squared over 2, right? This is v squared over 2 going from 5 to v. Okay, now that's correct. Okay, so let's go a step further. This is v squared over 2 minus 25 over 2 is equal to x squared plus 3x, right, minus 10 squared, which is 100, right, minus 3 times 10, which is 30. Okay, let me bring up a new page. All right, so let's simplify that a step further. I'm going to solve for v squared here, right? So I end up with v squared is equal to 2x squared plus 6x minus 2/6